So yeah, I'm Peter, if anyone doesn't know me yet. And I'm going to talk about preprojective algebras. I think this is not a full 2-hour talk, hopefully. And so I wanted to start by, from the point of view of some of the things that came up in Tony's talk a few weeks ago. So there we had the following setup. So gamma is a subgroup. I have V over C is a two-dimensional vector space, and gamma is a finite subgroup of SLV. And probably we don't really care about the case where it's the trivial group. So for finite. And so these groups are classified. So you have three choices. You have gamma is cyclic, which is type AN. You have gamma is a double cover of a dihedral group, which is DN. And then you have gamma is E6, E7, or E8, which correspond to the tetrahedron, the octahedron, and the icosahedron. So I'll just say a little bit about the assumptions. So here, probably the most important part about C is that it's characteristic 0. Maybe the next most important thing about the complex number is that it's algebraically closed. If you were to do this over another field, like maybe if you wanted to do it over R, then you don't actually get many more examples. Well, actually, many of these examples don't even exist because they're not defined over R. You get fewer examples, yeah. You get because the maximal complex subgroup of SL2R is a circle. So you only get finite subgroups of the circle. But they should actually be part of this story. But I won't include it as part of this story. I don't want to work in positive characteristic because I really want the representation theory of gamma to be semi-simple. So that's sort of just a comment. And so what does one do? If you listen to Tony's talk, you consider the symmetric algebra of the vector space smashed with the group. And I'll explain what that is. So you want to consider this. Maybe I'll just write down the general definition of a smash product. So if you have A is an algebra and H is a Hopf algebra, e.g. a group algebra, acting on A, then you have the smash product is A smash product H as a vector space. It's the tensor product, and the multiplication is A tensor H times A prime tensor H prime is A H1 A prime tensor H2 H prime. So here I'm using the Sweedler notation for the coproduct in a Hopf algebra. So the coproduct of H is H1 tensor H2, but it's really a sum. And then you really have a sum here. Okay, and this, of course, gamma, this, I'm just being lazy and dropping the C of gamma from the notation. This is the same as as this smash product algebra. And sort of why we considered, or why it was considered, it was so you can see Tony Licata's talk when this is talking about the resolution, the minimal resolution of the Kleinian singularity. And the singularity is just C2 mod gamma. But that's all I'll say about that. Okay, so the way I want to introduce things is to try to come up with another description of this, or more accurately, something that's Merida equivalent to this. So, and that's, so maybe I'll just say question. Let's describe this or something Merida equivalent to this in a different way. So, but no, before I want to say that, I will introduce, yeah, I'll just state the Mackay correspondence because we'll need it, or you will use it. So question is to understand this smash product algebra in another way, but let me just give a recollection on Mackay correspondence. So what you do is you take gamma, a subgroup of SLV, then and then let's let Wi, as I runs over some index set, be the irreducible representations of gamma, and you look at what happens when you tensor product with V and see what the direct sum ends are. So you define a graph. And it has vertices are the set I, and the number of edges between I and J is given by, you look at the representation Wi tensor V and look at the multiplicity of the representation Wj in that semi-simple module. And this is a little exercise, proof that it's symmetric in I and J, this description. So this is a graph, and the theorem is that this graph is an affine ADE Dinkin diagram and what else? And determines gamma up to conjugacy. Okay. Does everyone know this, or do you want the example? You'll know this. Good. I want to remind us because it's useful to have that. So my question here is, because we're going to use that graph, the question is sort of describe an algebra, Merida equivalent, to C2 mod gamma, with not C2 mod gamma, sorry, to S of V hash gamma, but with one-dimensional irreps. Such a thing is usually called a basic algebra in the theory of finite dimensional finite representations of finite algebras. This is not a finite dimensional algebra, but it's close enough. Okay, so one way to approach this is very simple. I can take, well, these WJs, or these WIs, firstly, they're irreducible representations of gamma, but they're also naturally irreducible representations of this algebra where V acts trivially. And they're all the irreducible representations. So what you can then, of course, do is you can take a projective cover, say, and then this is Morita equivalent to, say, the endomorphisms of a direct sum of the projective covers. And this is the algebra that we want to try to understand. You can also write it, of course, as E for an appropriate idempotent. And EI is a primitive idempotent in the group algebra of gamma, which corresponds to the representation WI. So maybe this is obvious and maybe it's not, I don't know. So I should also say, I didn't say this before, but this is graded. By just taking gamma, of course, has to be in degree 0, the group algebra, and V is in degree 1. So in degree 0, this is, if we look at this thing, so in degree 0, this is fairly simple. In degree 0, this becomes E times the group algebra times E, and because of the choice of this is a commutative semi-simple algebra. So degree 0, it's just a direct, it's a direct sum of copies of C. So what happens maybe in degree 1? Question mark. So yes. So if I let's say I look at some let's just do a computation so that we're familiar with it. Let's say I take one of my idempotents and I do something like this, then where H is in gamma, I mean, like really, I should use gamma, right? Then this is really in the tensor product description. This is really like 1 tensor EI, E tensor gamma, 1 tensor EJ, and this becomes. This actually doesn't actually depend on where V lives in which degree so far. And this becomes, where is it? It's EI1, V tensor EI2 times gamma EJ. And so as they vary, this thing becomes a generic element in WJ, this little, not the whole thing, just this gamma EJ. That's because gamma is in the group algebra. And let's say that if V is in V, then this of course lies in V, and this is the formula for how the idempotent EI acts on the tensor product. So let's go over here. So this is, oh, I moved the board. This is EI acting on the tensor product V tensor WJ. And so the size of the space that you get when you look at all these elements, and you get, I'll write it as HOM WI V tensor WJ is isomorphic, I guess, to EI V. And is this degree 1 part of the algebra. You get these home spaces occurring, and you recognize that, of course, as telling you the dimensions of these multiplicities. Now, so this Mackay correspondence is coming up naturally in the degree 1 part. So in degree 1, you get the doubled Mackay quiver. So what that means is that for every edge I and j in the Mackay quiver, you get an arrow in each direction in the degree 1 part of this algebra. So a basis element in each direction. So what we want to do is present this algebra as this quiver modulo some relations. Like the path algebra of this quiver modulo some relations. So maybe I'll give this a name. Let's call this quiver, call this Q. Q bar. And so you have that this is Morita equivalent because this is clearly generated in degree 1. Yeah. Because the symmetric algebra is generated in degree 1. So this is Morita equivalent to the path algebra of this quiver modulo something. And the question is, what is that? And I want to tell you that that's the preprojective relations, if I have time. I've lost it. All right, so I'll tell you what I know about this story, at least. So where might a relation come from? Well, it's probably a good idea. So since I gave the arrows in terms of this language, I might say something about how you actually compose these arrows. So if you think about what happens if you go up into degree 2 with this type of argument, because you've got the symmetric algebra here, you're going to have things like a symmetric square of V here. So you're going to be looking in degree 2 at things which have Homs from Wi to a symmetric square of V tensor Wj. So I'll explain how to compose these arrows. Or at least how to compose the generating arrows, and you can check that it works. So if I have two of these morphisms, and I want to know how to compose them in my algebra, of course, I can't just compose them as linear maps because their domain and codomain don't match, but I can take the following. I can take Wi, and I can apply F, and I get into V tensor Wj, and then I apply the V tensor, or the identity of V tensor G. I end up in V tensor Wk, and then I project into S2 of V tensor Wk, because V tensor S2 of V is a quotient of V tensor V. And this is my composition in this algebra. Okay. So now let's actually at least see where some relations can come from. So let's forget about the really small case where you get a double bond. I don't want to think about, I mean, it's such a small case, you can do the exercise yourself and do the example in that case. So let's, is the word a simple graph when you don't have any double edges? Yes. So suppose the Mackay graph is simple, which is no double edges. And this happens except for just the cyclic group of order 2. So i.e. gamma is not this silly central group. And then let me write di for the degree of I. So I'm going to make a claim for you about the representation theory, the degree of the vertex I. So the claim, and you might all think this is obvious, it probably is. So then if you look at multiplicity of Wi in S2V tensor Wi, then you get di minus 1. So I'll explain where this comes from. So if you first, the way that I would prove this, if I look at V tensor Wi and look at that multiplicity, well, if I think about that from the Mackay correspondence, I first look at all the places I can get to from in V tensor Wi, and then work out the ones how I get back to Wi. So this, of course, is a direct sum of Wj, and there are d copies in this direct sum, di copies in di terms, because that's by definition. And then each of these terms gives me a Wi back because the graph is symmetric. Because of the symmetry in the Mackay graph that I didn't prove. So this becomes di. And then the other piece of input, of course, this is sim2 direct sum wedge 2. And well, as gamma is a subgroup of SL, the exterior power of V is just a trivial representation. So you have to subtract 1 when you chop off the exterior tensor W. So you have this, right? And then, so I claim that this is going to tell me that there's a quadratic relation at each vertex. So so let's just draw a vertex here. So here's what my quiver Q bar might look like. I mean, I can even try to give a real example. I'm not sure that was a good idea. Um, 1, 2, 3, 4, 5. Is this E6 affine? Yes. This is a real example. So here's an example, and let's say I look at the central vertex. Well, here I've got 3 paths of length 2 that start at the central vertex and finish at the central vertex. There's this one, and this one. But the space of maps of degree 2 from the central vertex to itself has to be 3 minus 1, which is 2. So they must be linearly dependent. So we have at each vertex, you get there are di paths of length 2, starting and finishing. But the degree 2 piece in the algebra has dimension di minus 1, so therefore there exists a relation. So these are the relations. And these are actually going to be all the relations in this algebra. So this soft argument tells you it points at the existence of a relation. It doesn't tell you what the relation actually is, although of course it's a linear combination of these 3 to 0. But we never even actually decided what these arrows are up to scaling. There's a lot of freedom in terms of rescaling the arrows. With a little bit of work, you can show that in this case that all the coefficients are actually non-zero, and then you can basically scale the arrows as you want. In type A, you have a cyclic quiver. You have to do a little bit more work, I guess, here to work out what the relations are, because you don't have as much freedom when you try and scale the relations to make them fit what you want. But type A is sufficiently explicit that you can just write anything down and work out what they are explicitly. What else did I want to say? Yeah, so now I'm just going to tell you what these relations are. I'm going to define the preprojective algebra in terms of generators and relations. And this is actually much more general than affine type only. So let me do it in full generality. So now we're going to define preprojective algebra. So the way this starts is first you start with Q is a quiver. So a directed graph. And then what we do is we take a double quiver. So that if your quiver is like this, then your double quiver, you double the arrows, but each doubled arrow is in the opposite direction, which is exactly the style of the the quiver that comes up in this Merida equivalent algebra. So then I need a little bit of notation. So, okay. So this gives you some sort of just notation. This gives you a natural involution on the edges of Q bar, which I'll write as A goes to A star. It turns this rightward arrow to the leftward arrow and vice versa. What else do I want notation-wise? The other thing I'll say is that I'll write epsilon of A equals 1 if A comes from the original quiver. So here A is an edge, and -1 if A is a doubled edge, if it's an original edge or a doubled edge. All right, so what do I want to say about, and then I just want to define an element. So what I can do, I can take, if for each vertex I, I can define some element, which I'll call maybe rho I, and it's a sum over all arrows which start or end at I. I don't think it doesn't matter. It's up to your conventions. So the source is I. So I wrote down epsilon of A star A. So this is just a sum of all of these loops around this vertex with some plus or minus signs just sprinkled in because we like plus or minus signs. And then the definition is that the preprojective algebra is, I might call it, is the path algebra of Q bar modulo the ideal generated by these rho i's, the two-sided ideal. So this is some algebra. It has one quadratic relation at each vertex, and that's it.
So you argue that you have a map from this to this endomorphism algebra basically.
Yes.
But you're not having a class multiple.
I am, but I haven't stated that yet.
But where does the kind of, like, you've got.
I didn't prove it either.
No, are you sure it's correct?
I think it's correct. Are you asking where are the polynomials?
Yes.
Yes, that's a good question. They're not really visible, are they? Yeah. So A1. Oh, no, A2. What's A2? So affine A2. So affine A2 is this, and you can go round and round and round and round and round, and those are all linearly independent. I don't know, that at least proves that it's infinite dimensional. In the cyclic case, it's actually easy to write down a basis. You can look at like all paths that start off going anti-clockwise for a while and then come back going clockwise. And then you ever have one change of direction, and that gives you a basis in type affine A. I was hoping to give that as an exercise.
So the theorem is that these are, you have described the space value.
Yes. So I was going to say a few things about that. So I might, what do I want to say? I was going to make a remark or two about this definition. And then I'll state the theorem. So just maybe a remark about the definition. So one remark is that this condition is a moment map condition, and I just want to say that without going through the details because it might take time and people either know what that is or they don't know what it is. I'll just say sort of, did I write down what it is? No, I didn't. Oh, so this is a, so what's going on is briefly is if you look at, let's say I need a letter, I need a good letter. So let's say I look at, yeah, so I look at G is a product of GL of XI, where XI is some vector spaces, and then I look at EX, which is a product of arrows in Q, the original undoubled quiver of HOM XI XJ, then what you have is that G acts on T star of EX. G acts on EX by changing basis everywhere here and here. So it acts on the cotangent space. So maybe this is just an exercise. There's a moment map mu, and this condition is that, so the moment map mu always goes from T star EX to the dual of the Lie algebra of this group G. And then this condition is that, so a point in here gives a representation of the preprojective algebra if and only if its image under the moment map is 0. Maybe I'll just state that. Taking the cotangent space here is the same as sort of like doubling the quiver because the dual of HOM XI XJ is the HOM from XJ to XI. So the claim is that a point X in T star of E X corresponds to a rep of phi if and only if U of X is 0. So this is like an exercise for the interested reader. The other remark I wanted to make was that there's a completely alternative definition of this, which another definition is where you use Oslander-Reitentrace lengths. I don't know much about that at all, so I won't say that, but I'll just say that there's an alternative definition where you use something like where you take pi is direct sum over all n HOM in and these are the Oslander-Reitentrace, and that's all. If you know about this, then here's another way to think about a preprojective algebra. If you don't know about it, I'm just not going to mention it again for the rest of the talk. That's where the name preprojective comes from, because as a representation of the underlying, the original quiver, this becomes a direct sum of all the pre-projective representations of the original quiver. And then you need to know what a pre-projective means.
Simple steps, like that. Like all modules become kind of irreducible or something.
I think pre-projectives will eventually become projective under the Auslander-Wrighton. Or no, or will become simple. It should be projective. If it's,
but it's something like everything becomes something special. So like
yeah,
all modules
become projective if you keep applying it, I think. It should be projective based on the name. All right, so what else did I want to say before the break is I'll write down the theorem. So the theorem is that this first theorem is that the symmetric. Sorry? This is Morita equivalent. Can I throw them out? I've got lots of this. It's really good because if someone's snoring, you get it in their mouth and it. It's Morita equivalent to the corresponding preprojective algebra. So this is a theorem, and of course pi has to be for the correct quiver. And so far what we did, we basically modulo a few details. We got a surjection from pi onto this Morita equivalent thing. So I'll say what I know about how to finish. In type A, finishing is actually quite easy from here because you can write down, so in type A, the group here, gamma, is abelian, so this idempotent doesn't even appear, it's just the identity. And so it's easy to write down the graded dimension of this because you know the dimension of the symmetric algebra. And then you can easily write down a bound on the graded dimension of this because you can write down a spanning set, which is these paths that I mentioned when Geordie was bugging me about where you go anti-clockwise for a while and then go back clockwise. And it's easy to show that's a spanning set of paths. And so then you get that this is an isomorphism just from dimension counting reasons. Because this is generated in degree 1. Oh, when you cut by. Are you worried that when I cut by idempotence, I no longer get generated in degree 1? Oh, I didn't think about that. There's also the whole finite dimensional algebras equivalence relations point of view you can probably try and take, which makes it clear. Because these generators will correspond to X1s in the module category for this. I don't know the details of that thought, but if you know the X, oh no, that doesn't tell you generating. Yes. Let me say that's a good question. I don't have an answer to it right now. It's an issue that doesn't arise in type A. So in type A, I know how to finish because you can do a dimension count. And I actually don't know how to finish it in other types. I sort of tried to look in the literature and didn't understand what was happening, which is a little unsatisfactory. So here we're looking at this algebra, which is the endomorphism of the direct sum of the PIs. And if you put some multiplicities in, you get canonically the algebra back. And these two algebras have are generated in the same degree. So if one's generated in degree 1, so is the other. All right. The question was just that in the unlikely event that Jody makes just so. So there was a question for the Zoom for the benefit of the Zoom audience. There was a question about why the idempotent truncation preserves the generated in degree 1 property. So the question as to why pi actually suggests here, where the argument was that, well, this is generated in degree 1, and it's because the idempotent truncation is this direct sum of this endomorphism of a direct sum of projectives, but you just take the endomorphism of a direct sum of projectives with different multiplicities, and you get canonically the algebra back itself. And so, and these two things are clearly generated in the same degree. I hope that they are. All right, so let's continue. And part 2 is kind of different from part 1. So that's all I was going to say about this S of V smash gamma and its merger equivalence with the preprojective algebra, because I don't know how to finish in type D in it, which is a little disappointing, but I think the literature is, I'm going to blame the literature for being lacking in detail. So there's this statement by Crowley, Bovey, and Holland, and they claim to also do it for a deformed version of both algebras. And then they also say that the computation, at least in this particular case, is essentially due to Wrighton and Vandenberg, in like just hidden in some proof apparently, which I didn't really follow. So, and I don't know if there are other references. Okay, so so part 2, I'm just want to sort of talk about some sort of more, some rep theory. Of just say a few things about the representation theory of the preprojective algebra and some general facts that maybe you think are cool or not cool. Yeah. So and here we're going to work in general type. All right. So we can just start off even with an example if you want. I mean, there's actually a dichotomy in the representation theory of these algebras. Sometimes you get different behavior depending on whether you're in finite type or if you're not in finite type. I mean, maybe that's not surprising, but really you see different behavior in the preprojective algebra in those cases. So maybe if I'll just write down some modules for A2 just so you can see what's going on. So A2 preprojective. So that means that I've got, this is my double quiver, and then I've got some relations. So in this case, it's small enough that it's a finite representation type. There are a finite number of indecomposables. So I'll just write them down. And as an exercise, you can verify this. So let's write down the indecomposables. So firstly, you have your simple modules. So there are 3 simples. These are simples. So they're one dimensional. So I'll just draw them in positions 1, 2, and 3. This is 1, 2, and 3. They're one dimensional. They're not very interesting. Then you've got a few 2-dimensional modules where you have one non-zero arrow. And if you've got this arrow is non-zero, then the preprojective algebra is going to force the arrow in the other direction to act by 0. So here, this picture means I've got a one-dimensional vector space at 1 and a one-dimensional vector space at 2, and an arrow from this one, which is non-zero map. Or it's the identity map, whatever you prefer. So you can check that and so of course you can do this in either spot, and you get 4 two-dimensional indecomposables. Of course, you can continue this, and you can do some 3-dimensional indecomposables. This one is projective injective. So part of the exercise is to prove that. Then you also have this one, which by symmetry is also projective injective. So here I've got, and again, like once you've got this, the other arrows are going to be forced to be 0 by the preprojective relations. And then you've got 3 more. One is, looks like this, which I call in, because the arrows point in. And one which looks like this, which is out. And the other one is this 4-dimensional. There's a 4-dimensional one which looks like this, which is also projective injective. So you also see a few things. So exercises to prove everything that I mentioned there, that these are actually injective, for instance. And the main, and you see a couple of things like that. This algebra is, so I didn't point out, but this algebra is finite dimensional. You see the projectives are finite dimensional. And also that it's self-injective, which means the projectives are the same as the injectives. And those two things are specific to finite type. So just for finite Dinkin quivers. So here you see finite dimensional and self-injective, which is true if and only if the quiver is finite type ADE.
So does that statement, how does one read that statement?
The preprojective algebra is finite dimensional if and only if it's a union of ADE, and also self-injective in those cases. I don't know.
Finite dimensional implies ADE.
Yes.
And also implies.
And the other way around. Of course, you can have a disjoint union of ADE graphs and have something silly. But connected things are the only interesting ones. Okay, so
Peter?
Yes, there's a question in the ear. Continue, please.
So are all vector spaces one-dimensional, and are all maps identity?
So the question is, are all of these one-dimensional, the maps, the identity? Yes, in this example, I think. This one here, I guess you have a 2-dimensional vector space at the 2 vertex, and but it's split up in a way that I can write it as a direct sum of one-dimensional things, and then these maps are all the identity. Okay. I want to try to explain something about why the rep theory of these preprojective algebra has something leaf theoretic in it. So maybe let's do that. So let's say I have let's say I have M is a finite dimensional representation of pi. And then I can look at its dimension. So, but I want to look at its dimension vector, which should really be thought of as a sum of dimensions of the idempotent times M times some vector alpha I, which is just some formal symbol right now. It's a basis vector, and the notation is chosen in an evocative way. So this takes values in some lattice with basis alpha I, and I want to identify this lattice as a root space, a root lattice, or a weight lattice. I guess the root lattice lives inside the weight lattice, so we can put a we have a bilinear form on this space, which is the usual bilinear form on this so you have alpha I paired with alpha I is 2, and alpha I, alpha j is like the number of edges. So the number of minus the number of edges I to j or j to I in, just take the undoubled quiver, and then you get the usual Lie theoretic bilinear form on this, so we can start to talk about everything we know and love about roots and file groups and anything else that we like. So of course, from this, so far we don't see any connection to the representation theory. Like it's just there by itself. All we know so far is that the simple modules, of course, have dimension just alpha I. So alpha I is the dimension of the simple, but here's a formula for which shows that this bilinear form has a representation theoretic meaning. So let me just write down a theorem. It feels a little maybe unmotivated or abstract, but it gives a representation theoretic incarnation of this bilinear form. And it's I've heard it called the Crawley Bovee formula. And so it says the following. So if I have two representations, of pi, which are all representations from now are going to be finite dimensional, and all representations are graded, because I didn't say that before. So then if you look at this, this inner product of the dimension vary, because it does have a homological interpretation, and it maybe is not what you might first write down. It's dim. So that first term maybe is not surprising. The second term is maybe a little less surprising. And then you have the third term, which is actually not surprising. And that's it. Ah, yeah. It is very surprising. Thank you. So yeah, you have, I mean, the first and third term now are kind of what you might expect, but you end up with this alternate term in the middle where you have the harms in the other direction. So one corollary of this is, of course, that this thing is symmetric. Sorry? Oh, there's no Q's here. Ungraded. Oh, I didn't want to deal with any
Yeah,
ungraded.
can I ask about whether pi is not hereditary?
That's true.
So in principle, there could be an x2.
Yes. In principle, there could be an x2. In fact, like if you look at this example here, this one is infinite global dimension. Yeah, so it is, I said, this is a little surprising, this term. I was going to mention one consequence that you see, at least from this formula, which is that this is symmetric in M and N. These two terms are symmetric in M and N, and this is not symmetric in M and N. So you can see you get as a corollary some x1 symmetry in the dimension level, but actually it's even stronger than that. So maybe I shouldn't call it a corollary. You also have that the is the dual of the x in the opposite direction. I can say where this comes from, as in how you can prove it, and then you can decide whether or not that's a useful explanation or not. I don't know anything about x2. No, I think so. Yeah, something's 2 Calabi-Yau. I don't remember what 2 Calabi-Yau means. Oh, okay. But does that tell me that, are you saying that this is then an x2 of mn? Yeah. But then you would expect there to be an x3. It can't have infinite global. Oh, maybe this.
I think that if you think in terms of the Mackay correspondence,
Yeah.
this is coherent tree supported on the singular bit. And so it's like, it's a non-finite global dimensional thing that has a sitting inside a derived category that's beautiful to Calabi-Yau.
Jordy made a comment for the Zoom people, and I didn't understand what it was.
I mean, so here's a question. What does this all mean under the Mackay correspondence?
Jordy's now got a question about what does this mean under the Mackay correspondence, and I don't know. Sorry. This is trying to be a learning seminar.
Can I just say what, perhaps it's helpful if I just say what I think it is?
Yes.
Because I'm reasonably sure that's correct. So if you take, EV of the minimum resolution. And now, so that's a beautiful 2 Calabi-Yau.
I'm writing, for the purpose of people in Zoom, I'm writing what Jordy is telling me to write. This is the minimal resolution of a Kleinian singularity, which is a 2 Calabi-Yau derived category.
So now inside this, you take the fully derived category consisting of complexes supported on the exceptional levels.
So here I'm looking at a full subcategory, which is say T, which is complexes that support the exceptional locus. And so this is apparently a theorem, question mark, that Jordy is claiming is this is the derived of, and now this is the affine preprojective algebra, or the finite. Oh, this is, there's some argument in the chat in the room about whether this is a finite or affine preprojective.
periodic diagram that corresponds to the P1.
So you're saying that the structure sheet of the P1 is going to correspond to a simple.
Yes.
So then it should be affine, presumably.
I think it's affine, and then you take the subcategory that has a certain chronological. Yeah. It's some subcategory.
Okay. I don't have anything further to say about that. Nothing. I don't know. Oh, the homolog. Okay. Yeah, I only looked at the like how to prove this and not how to see it conceptually.
Yeah, so the bottom one is not good. No, the bottom one is
It's not equivalent, it's a full subcategory. So it could be or it could not be. We have no information. So this is a remark that Jordi made, and I'm not quite sure what it's got to do with what I was talking about, but it's an interesting remark anyway. Right. So the sort of way that like cavemen like me would prove something like this is they'd write down a projective resolution. So maybe I'll just say that you can write down if you want to try to write down some resolution. I won't write it down in complete. I won't write it down in detail because resolutions are not always that fun to write down. You can try to write down some resolution of the algebra as a bimodule over itself, and you get sort of this obvious term, and then you get a term which corresponds to the generators. And I won't write down the maps. And then you get another term which is going to correspond to the relations. So here you see generators, and here you see relations. And so this is giving you some sort of projective resolution of this. And so what you can do is you can apply, so I'll just sort of sketch how you might prove this. So if you apply this, if you tensor with m over pi, you of course get rid of all this pi, etc. And you get a projective resolution of m. And then you apply, then you want to compute the derived Hom, of course. Then so you apply R. You want to compute the Hom into n, and so you end up with some complex. You end up with a complex which looks like the following. I wrote it down. I don't think it's important, but it's after a little bit of work, which is really simple. You get some complex like this, and its H0 is this first term is the H0, this second term is the H1, and this is H2, and you see that it's H2 because you get this some symmetry by swapping the order of M and N if you took the dual of this complex. That's sort of where how the proof comes in quickly. You can sit down and go through the details of that if you want to. And it's quite clear that this these HOMs are all over the complex numbers, and these are just HOMs of vector spaces. So you get immediately this thing on the left-hand side. So since we don't have much time, I won't say everything that I want to say about representation theory of pi. Tony mentioned some no. I thought in finite type it was infinite, and that in affine type it was 2. Elijah, I think I'm trying to answer your question. So I was under the impression that in finite type, the preprojective algebra had global dimension infinity, and in affine type, I think it has global dimension 2.
Okay, thank you.
And I'm getting some
You said
nods from the audience.
but I understand, I think. The thing you drew was finite.
The thing I drew was finite, yes. The
Okay.
exact finite things are easier to write down. Yeah,
I understand.
I think in non-affine type it might be 2 as well. The question is really whether or not this is injective. I'm not going to try and think about that off the top of my head. Yeah, so you do see some significant differences between finite and affine type. Yeah, so this behavior, I guess, now it's making more sense to me. This is x2 in affine type, but in finite type, this is a formula which is still true. So I remember that Tony mentioned one thing that Tony mentioned, and I'll just say this verbally, is that there were these like nice representations corresponding to other roots, not just the simple roots. And my understanding is that you can get them from applying various reflection functors to the simple roots, but I won't go through that. I think I'll just say a few things about, I hope I'm not repeating myself, about maybe one of the more Lie theoretic theorems about representations of pi. So this is maybe old news to some people in the audience, but still let me sort of say that at least explain the results about how you can realize crystals in representations of pi. So this is Anthony's probably like, I've seen this before. This is like Kashiwara and Saito do this. I guess Lustig also does some of this work, so some related stuff. So maybe I should have his name as well. Although the main, all the results with crystals are the Kashiwara Saito stuff. So I might just sort of say what the tell you what the results are, and then we might be out of time. So let's say I have, so let me first give a definition because I need a definition. So a representation is nilpotent if all its simple subquotients are these vertex simple modules. So this is, so if you're in affine type, I think if you look at non-graded representations of the preprojective algebra, you can get simples that are not one-dimensional, and we don't like those. Like you just go around in a loop or something in type A, and you have that act as something non-zero, and we don't like that. So so yeah. So and then if you take if nu is sum of nu I alpha I, then what you can do is you can let lambda of nu be the variety of representations of this preprojective algebra on a vector space of dimension nu. So it would be I graded dimension nu. So concretely, you have a vector space which is dimension nu I at each vertex, and then you're looking at spaces of maps that satisfy the preprojective relations. And so the various theorems. First theorem is that this is an equidimensional algebraic variety. So one ends up, and we want to look at its components. So what I can do is I can look at some functions. So I can consider this following function. So this is a function where you put in a representation and you output a number. It tells you the number of occurrences of this particular simple in the socle of the representation. But this is a semi-continuous function. In the sense of algebraic geometry. But in particular, that means that so on each component, it takes a generic value. So we'll call this phi I of z. So you get this number phi I of z, and then similarly you get phi I star from the other order. Same argument, nothing changes. So now I'll also define some other information. So now let's take some let's take Z to be some irreducible component, and then I can take some X, which is a module, take X generic, and then I can look at, so I can consider a generic extension of X as follows. So 0 to SI to Y to X to 0. So you take some sort of generic extension by a simple, and then there's some work to do. But if you look at these Y, then they will be generic in some other component. Your dimension has, of course, increased by alpha I. And this gives an injection which I'll call epsilon I, no, EI, tilde. Between irreducible components at one weight and irreducible components if I increase the weight. So maybe we're seeing what's happening. This is a crystal operator. Oh, I don't have any time. Yeah. There's always a generic extension. Maybe the generic extension is split, but you can always take the most generic possible extension. Yeah, so I want to say that, and then similarly, you can define using extensions in the other order. So, does everyone here know what a crystal is? It's too bad if you don't. So I might just state that the theorem is that this set, the union together with these IIs is isomorphic to the crystal B minus infinity, which is the crystal of a Verma module. This is a, I think I did lowest weight. Did I do lowest weight? Yes, because the E's are always acting. So this is the lowest weight. Verma crystal. So of course, in a crystal, you have a weight function from your objects to the root lattice, but that sends a component that just reads off nu. And then you have these crystal operators, EI tilde and epsilon and EI star. There are two because it's B infinity. There's a star and an unstarred. And then you also have Fi, which is the partial inverse of EI. And then you have these numbers, which record various data about the crystal. And
Is it correct to think about this as being the tonal bundle to the orbits of rep? Like I can just look at rep of my finite quiver.
yes.
And I can look at, so that then because I'm a finite ABE, I have a finite degree orbits of this. Then I can look at the union of
All the conormals. Yes, I believe that's the same thing
Yeah, it's true
for finite type. For non-finite type, because you have, like, you don't have enough, or you have infinitely many orbits. So I think
that,
you're right.
Gives you some intuition of why the numbers are at least correct. For every dimension,
Yes.
the cosine function.
I guess that gives you some intuition if you know what happens in the finite type. Yeah, case, yes. But
Did you impose the latency condition?
oh, I forgot to write it. Yes, there should be nilpotent in the definition of this.
That's automatic, probably.
It's automatic if it's finite type, but it's not automatic outside finite type. But all of these representations are going to be nilpotent because everything is generically extended by, everything is built up from extensions of these simples. So how long have I got? All right. I wasn't going to, I'll just say that I want to write down because I think it's cool. Maybe I wrote this down. I don't remember what I said in my last IFS talk. And I hope I'm not repeating myself. But there's another theorem, which is a characterization of this, which is kind of useful in proving these sorts of identities. So I'll just mention this, which is a characterization which is due to Kashiora and Saito, but they don't write it down in exactly this way. This is a sort of a different presentation of the same result. So it's, yes, I did write it correctly. I was just hoping that I didn't have to translate between highest and lowest weight. So let's say I have B, I have a B, a weight function, and EI, and EI star, and FI star, and phi I star. So that sounds like a lot of data, but you have all that data. Satisfy the following conditions. So this one are lowest weight crystals with the same lowest weight vector. So that's of course satisfied in this case because the lowest weight vector is the case where mu equals 0. And then there's this bunch of conditions like that. Firstly, I guess and never this 0 element. So this is something which should be true in the B infinity crystal. There's obviously a question from Mr. Jacobi or Williamson. Yeah.
I mean, we
There's a star involution on B infinity, so you don't need it, but it's used in this characterization. Yeah, but it's not important, I think. No, it's some teaching crap. If I is not J, then you get this commuting behavior. Then you get some inequalities. I'll just write them down for completeness. This inequality in our case is Crowley-Bovey's formula. This becomes the dimension of an x1. Proving this is bigger than or equal to 0 in other realizations of the crystal can actually be rather non-trivial to do directly. So that's kind of magic there. And then if I should give this a name. So let's call it let's call it n. If n is equal to 1, then you get some extra conditions. And similarly, I think I've lost some tildes, but don't worry. And if n is at least 2, EI star EI B is EI star B. And once you've got all these conditions, then the conclusion is that you actually get B infinity. Then with the and there's a Kashiwara star involution on B minus infinity, which sends one to the other. So I just wanted to mention that because I think it's a useful result to sort of know about, maybe. And that's how you prove this. I realize that we didn't get through a lot of detail, but this gives you a geometric realization of the crystal in terms of representations of the preprojective algebra, which is one of the earlier results about the preprojective algebra in a more Lie theoretic framework rather than a representations of finite dimensional algebras framework. So I'll stop here. Thank you.